In the previous video, we have talked about how occupancy impacts the performance. But sometimes we cannot easily tune occupancy. Assuming we have a lot of threads running in one compute unit, then how can we better utilize all these ALUs? There's a key concept called thread divergence. Remember when we talk about GPU architecture, how GPU handles divergence. If we have an if condition and only half of the thread in one wavefront will follow that if condition, then the execution mask will have 32 ones and 32 zeros, and only those 32 threads will take effect. But the calculation actually needs to be done on all 64 threads. Then the ALU utilization on this particular instruction becomes 50%. In extreme case, we only have 1/64th of the ALU utilization. That is something we want to avoid. So in this video, we're going to use this example of sum of non array to see one method that can reduce the thread divergence and improve ALU utilization. So let's look at this example. The goal is to use as many ALU as possible, but some algorithm may not be that suitable for GPUs to exploit all these ALUs. For example, we have this program that calculates the sum of an array. It's a loop that iterates through all the elements in an array and will keep accumulating into the sum. And the sum variable is a dependency between each iteration, so that prevents us from converting these loops directly into a kernel. So the easiest way is to serialize the execution, and we can only have one thread to execute. In this case, this program is basically the same as a CPU program. And we measure the execution time on my 50 GPU, and the execution time is 0.58 seconds with 10 million data points, which is much slower than a CPU execution. So what can be a reasonable optimization? So considering the fixed size of kernel, you may come up with a solution that we may have local sums, right? So we may have each thread to calculate the sum of the subset of an array. In this case, if we still have 10 million data points, we can actually finish the whole kernel in 78.1 microseconds, which is 7,300 times speed up. But you may get a question, at this point the output is still an array. We can see this output index equals sum, right? So assuming if we have 10,000 threads, then our result is an array of 10,000 elements. Then we still need the CPU to sum them together, which may introduce some extra overhead. So what we can do to continue to optimize this algorithm? And the solution is to use a reduction algorithm. So the reduction algorithm for GPU is depicted in this picture. Assuming we only have 8 threads in one wavefront, then we can use thread 1 to calculate the number that belongs to thread 1 and thread 2. We can use thread 3 to calculate number that belongs to thread 3 and 4. And thread 5 for number in thread 5 and 6, and thread 7 for the number in thread 7 and thread 8. Then we're reducing this problem from 8 numbers to 4 numbers. As we keep reducing it, every time we reduce it to half of the number. Eventually, we get one number in one block. So assuming if we're using a block size of 1024, then we're reducing the whole array that needs to be summed by the CPU by 1000 times. So how can we implement this reduction, and where do we store the intermediate result, and how we can let each thread to access the data that belongs to another thread? This is something we have never done until this point, but luckily we have something that is called local data share. So local data share is both a software concept and a hardware concept. In terms of software concept, it is a part of data that is addressable within one workgroup. It can be used for wavefront to wavefront communication or thread to thread communication as long as the threads belongs to one block. It is also a hardware concept. It is implemented as SRAM, the same technology used for registers and L1 caches. It is part of the compute unit, so it is physically very close to the SIMD unit. So loading data from LDI side is almost no latency, 1 to 2 cycles latency. And the throughput is very high because there are a lot of wires that are connecting the LDS with the SIMD units. So we can consider LDS in this way. It is a programmable L1 cache. As programmers, we can decide what data to store in the L1 cache that is named as local data share in this case. So let's look at an example of calculating the sum about how we can allocate shared memory and how we can utilize the shared memory and how we can avoid pitfalls. So let's see this example. The first line in this code, we allocate a memory using this shared modifier. So the compiler knows it's local data shared memory. We call it shared mem. This is a variable, you can name it whatever you want, but we need to specify the size. And this size is per block. So here we use this Markov block size to be consistent with the block size, which is the number of threads within each block. If we have a block size of 1024, then the shared memory is also an array of 1024 elements, which equals to an array size that is managed by this block. Then, in the fourth line of this kernel, we use shared memory LID equals input GID. So here, LID and GID are two different identifiers. LID is the local ID, is the identifier within the block, and the global ID is the identifier with respect to the whole grid. The input GID identifies which piece of data that we want to load, and we store this piece of data into shared memory. As you can see, reading or writing shared memory is nothing special, it's just the same way as accessing global memory, but the performance is actually much higher. After loading the global memory and storing in the shared memory, we can start to do the sum operation. In this case, we have this for loop. This for loop basically implements the algorithm that is depicted on the figure on the left. The minor difference is we're using thread 2 to calculate the number. The only minor difference is which thread we're actually using, but the theory is the same. And finally, see the if statement at the end of this function. We use if LID equals to 0 to select the one particular thread and within each block, and we write the final result into the output. So right now, if you run this program in a GPU, you may get some wrong result. So let's try to analyze what may be the problem. Let's say if we had two wavefronts running this kernel, and one wavefront may be running this shared memory LID equals input GID line, and the other wavefront may not be even started. So if the faster wavefront completed this line of code and continue to move forward, and it will start to run this shared memory LID plus equal to shared memory LID plus S line. But this S line may be accessing the data that is supposed to be loaded by another wavefront in the shared M LID equals input GID line. In this case, we may have a synchronization problem. We want all the wavefronts in one block to finish this shared memory LID equals input GID line before we executing this for loop. It's the same way when we talk about this shared memory LID plus equal to shared mem LID plus S line and the line in the last if statement. We need synchronizations. How can we do synchronizations? And he provides built-in functions called think threads. We want to use these think thread functions to synchronize the wavefront. These think threads are also known as barriers, so that all the wavefronts will arrive at this barrier, then all of them can pass this barrier at the same time. And be careful when you use barriers, it's generally not a good practice to put barriers in an if statement. If some wavefront will execute it and some wavefront will not execute it, it will cause a mismatch in the barrier. So the heap program will not really tell which barrier you are synchronizing. It will only reach one barrier, then all of them will pass at the same time. So if you write this barrier in one if statement, you may have a problem that one wavefront is synchronizing at the first sync thread while the other wavefront is synchronizing at the second barrier. Then it's very hard to debug the problem. So the general advice is to never put barriers in if statements. So let's put it all together. Let's see this reduction sum method in how we improve the performance and how these two methods can be used together. So see this part of code before shared float shared memory. we are actually using fixed size kernel to calculate local sums. Each thread is calculating the sum of part of the array. Now in the second part of this program, we're using a reducing method. This reduction method can significantly improve AL utilization to prevent writing serialized code or to dump the workload to the CPU side. And overall, as we run the program on MI50 GPU, the execution time is 80 microseconds when we're using 10 millidata points. It's similar to the local sum, as we add some code, but it doesn't really add a lot of overhead. But we reduce the memory copy time and we reduce the CPU workload.